Welcome to Transfer Phenomena Bioprocessing V2. So, aspects of rheology in the bioprocessing. So, the problem 2, last class we discussed the problem 1. The problem 2, just compare the column heights of water, then CCl4 and mercury corresponding to pressure of 50 kilopascal. So, of course, we know that one already. The last class we discussed P equal to H rho G, but the problem here, the density is a different, because here we used 3 different densities. One is the water, another one is a CCl4 carbon tetrachloride. The density is 1.59 gram per cc. Then the last one is for mercury, 13.65 gram per cc. So, when you want to use, and you have to use for only SI units, we cannot use some other units. So, what we have to do first, anyway, density of water everybody knows here, the density of water here 1000 kg per meter cube. Already the problem they given 1000 kg per meter cube. Then the density of carbon tetrachloride 1.59 cc. So, into multiplication of 1000, then we will get a 1590 density of carbon tetrachloride. Same way for mercury also. So, first we have to get the 3 density of values. So, once the 3 density of value done, so the pressure at is common, the pressure we can use the common pressure, the 50 kilopascal. Okay, then the only we have to find the here, compare the column height, the H of water and H of CCl4, H of mercury. Of course, the density value is already there. First you use density of water, then of course G value we know that one 9.81. So, get the value of first height of water. Height of water first we got the value of 5.1 meter, the first one. So, same way the density of we can use for density of carbon tetrachloride, use density of carbon tetrachloride and get the value of height, H of column height, H of CCl4. So, we got other one H of CCl4 3.21 meter. Then the same way for mercury also, already density of mercury is here already given the values, you just substitute and get the value of mercury height of the column. So, finally, we got the 3 column height, one is the water and the other one is for CCl4, then the last one is for mercury. So, if you want to reach this pressure 50 kilopascal, but you have to use the height of water is a 5.1 meter. So, the different height of column height to use to reach the 50 kilopascal, that is the problem 2. So, next is problem 3. This is again very simple problem. Okay, always we do lot of MATLAB programming, but to start the this one, so we have to start very basics. But I think the week 9, 10 sometime, okay, we will do lot of MATLAB programming if you are this one. So, here you just read the at what depth of below the surface of oil, then relative density is already given 0.8, will produce a pressure of 120 kilonewton per meter square. So, what depth of water is this equivalent to? So, they are asking first what the depth of oil, the first one. Second one, what depth of water? The same way here use P equal to H rho G. So, here the pressure is already given value already 120 kilonewton per meter square, but of course, we have to use the in terms of Pascal or whatever Newton per meter square, you always use the SI units, pressure unit, SI unit, do not use the different units. You check every units, always check all the units are same, then only we can use this here. So, the pressure is here already 120 kilonewton per meter square is there. So, in terms of Pascal, the pressure value already given here. Then of course, the relative density 0.8, you want to convert in terms of this one density, you have to multiply always the 0.8 into 1000, then we will get 800 of density of oil is 800 kg per meter cube. So, once this is done, then 9.81 is of course, we know that gravitational this one. So, the depth of oil we got 15.29 meter. So, only we have to find the H, rest everything we know already very well. So, first one we done for oil, the second one we are trying for water. Water density of water we know very well, density of water is 1000 kg per meter cube. Then okay, the P value here same way P equal to H rho G, pressure whatever we are using same value we are going to use here, and density is different because the first one is discussed the density of oil, but here density of water, the density of water is a 1000 kg per meter cube. So, the G is the 9.81 here. So, finally, we got the height of the depth of the whatever the liquid here. So, what the final conclusion here, when you want to lower the density and if you want to get the same pressure, so you have to adjust with the depth of required here. So, then only we will get the same, achieve the same pressure, because we have oil is there, then water is there to achieve the same pressure, but we have to adjust with the height of the column or height of the depth of the liquid that one. So, only we can get the same pressure of both liquids here, the problem this one. So, we will discuss same other one, that is a very simple problem again. Here the calculate the pressure itself they mentioned here kilonewton per meter square, and then at the bottom of a spherical tank filled with oil having diameter 8 feet here, the diameter is already given here. The top of the tank vented with the atmospheric pressure 14.72 psia. So, the pressure unit here. Then the density of oil here 0.922 gram per cc. So, here the depth is here, the depth 8 feet, we cannot use the feet, we have to convert always in terms of SI unit. So, 1 feet equal to 0.3048 meter. So, of course, you should know how to use the instead of other units, try to convert throughout the problem SI unit. So, that is very easy to solve the problems. So, what happened here, the same 8 feet here we converted in terms of meter, that meter is the 2.438 meter. So, then pressure is P naught value already there 14.72 psi. So, you want to convert in terms of psi to kilonewton per meter square. So, then finally we converted to 101.5 kilonewton per meter square. Since we are using here meter square, try to use throughout the problem SI units here. So, sometime we will ask the pressure is okay, different units are there. So, sometime we can write millimeter mercury pressure 760 millimeter mercury or 1.013 10 power 5 Newton per meter square. So, many units are there in the pressure, but all in the atmospheric pressure, but we have to use based on the problems here. So, the density again 0.92 gram cc, of course, we know it is a 922 kg per meter cube, the density also already done here. So, same way the hydrostatic pressure, the P equal to, we have to use the same formula H rho G. So, H already we know that one, the depth here 2.438, the problem, okay, the depth of that one, H already given the value, then rho density is here, the density of 922 there, G also there, you get the value of pressure here. So, already the P naught from P naught we already know the given problem 101.5 kilonewton per meter square. So, use the P naught value, then the delta pressure P value is here. So, add both together, then we get the pressure equal to 123.6 kilonewton per meter square. So, for we discuss some 3-4 different small problems, and then now we move for what are the properties of fluids we will use here, and then we will discuss one by one. Of course, you know that one, but this when you do transformation of bioprocess, and we have to learn for the basics also, without basics is very difficult that one. So, the pressure here, of course, we already discussed the P pressure equal to force by unit area F by A. So, we always write a Newton per meter square, these units, okay, that is only pressure is force per units. So, sometimes they use write Pascal, sometimes PSI. So, many we can use it here. So, example here if you want 1.013 into 10 power 5 Newton per meter square. So, you can write same way 1 into 10 power 5 Pascal, okay. And even if you want to convert in terms of 760 millimeter mercury, these all same, the different units are different, but in atmospheric pressure we can convert in terms of Newton per meter square to millimeter mercury here. So, even we can write for okay 14.69 psi, okay, and 30 feet of water, all are same, all units are same. So, but we can write different way, but try to use it throughout the problem SI units, because if you use different units while solving is very difficult to solve. So, the example here where you want to use the pressure here, the hydrostatic pressure in the fermenters, then the pressure drop pipeline, because when you use the bioreactor there is a pressure drop is there, then we have to measure the hydrostatic pressure also in the fermenter also. So, definitely we should have knowledge of pressure, how to this one. So, next is the temperature, everybody knows that where we will use here the measure of average molecular kinetic energy of the molecule in the fluid here. So, these units, okay, temperature units always degree Celsius, Kelvin, but only here then we even they can write Fahrenheit, Rankine, so many units are there, but normally we will always use the degree Celsius here. So, where we want to use the temperature here, the cell growth that depends on maintaining optimal bioreactor temperature, because when you want the cell grow, then we have to maintain the optimum the temperature, bioreactor temperature we have to use here. So, other density is a very simple density, we always call density equal to m by v mass by volume. So, we always write kg per meter cube, because just now we discussed some basics problems to understand for this one. So, density kg per meter cube. So, we can use kg per meter cube or pounds per feet cube, but you try to use for SI units. So, density is especially where is the problem here, the example microbial the cell suspension, okay, there we will use always this one. Of course, the density definitely affects the mixing and aeration. So, that is only the density also very important here. Then the specific heat capacity, we always write Cp specific heat. So, heat the required for to rise a 1 unit mass by 1 Kelvin, that we always the standard definition here. So, we always write the specific heat capacity is a joule per kg Kelvin. So, the specific heat capacity Cp is a specific heat constant pressure, then Cv specific heat capacity constant volume is there, but anyway mostly we will use for Cp, the Cp units here joule per kg Kelvin. So, where we will always use in our bioreactor process the cooling load in the fermentation process. The last one is the compressibility. The compressibility units the Pascal inverse, that is like pressure, reciprocal pressure units here. So, they measure the fluid volume and the change under pressure, that is called compressibility here. So, where exactly we will use for important for gases in the aeration system and high pressure fermentation, always we use for the compressibility is here. So, next one is for thermal conductivity, K thermal conductivity. So, here normally the thermal conductivity they will use for in the conduction units, conduction they always use, but we know already the famous Fourier's law of heat conduction, from there also Q by A equal to minus of K dt by dx. So, this is Fourier's law of heat conduction. So, there always we will use for thermal conductivity. The K units here watt per meter Kelvin, already is here given the value watt per meter Kelvin. So, in terms of some other units you can write a British thermal units here, but try to use always SI units. So, that is easy to solve for us here. So, where you will use the thermal conductivity, because the heat exchanger is a main here. So, there is a different type of heat exchanger, one is a double pipe heat exchanger, then shell and tube heat exchanger, different type of heat exchanger, how we use the sterilization process. So, definitely we have to use for thermal conductivity, that one. So, next one is viscosity, that is a very important here, whenever if you study the flow, but definitely the viscosity is the main role of that one, it play also here. So, the definition here, resistance of the fluid to flow. So, example shear stress versus shear rate always. So, the units always write this Pascal per second, then centipoise, or we can write kg per meter second, okay. These are also standard units here, okay. So, where they will use for this one, whenever the oxygen transfer is there, no, mycelial broth of this one, you always use for oxygen transfer, the viscosity is the very important to use here. So, the units here kg per meter second, and then Pascal per second, centipoise, these are the different units, but we will try to use always SI units how to solve that one. So, we always viscosity we write always mu. So, next one is for diffusivity. These are the basic property we use in our bioreactor, that is only we want to discuss diffusivity. Diffusivity is the rate of mass transfer due to molecular motion. So, we always write D is the diffusivity, the unit is meter per square per second. So, this is a very famous fixed first law is there, the J equal to minus of D dou C by dou Z. So, this is a famous fixed law is here, the fixed law, one is a flux, okay, mass flux, other one is a concentration gradient. So, when you want to replace, then we will use for D minus D. This D is called diffusivity, the unit is here meter square per second. So, these are different unit here, one is a thermal diffusivity, then mass diffusivity, momentum diffusivity, many diffusivities there, but this one is we are discussing here simple D, okay, that is only mass diffusivity. So, thermal diffusivity also that will be discussed one by one, okay. Then here where you will use for here the oxygen diffusivity into culture froth determines the oxygen uptake rate OUR we will say, okay. There always we will use for the diffusivity here. So, other one is for surface tension. The surface tension always we write here force by unit length, force by unit length. So, the unit always Newton per meter, the surface here. They always will discuss about the fluid interface here. So, where here especially the bubble formation in the sparged bioreactor we will use always here. Definitely the surface tension will affect the gas and liquid mass transfer. So, what we discussed already, that this the first one is for here, that we discussed about the mass diffusivity, then this is the thermal diffusivity. Thermal diffusivity we always write alpha equal to K by rho Cp, but all units are same, the thermal diffusivity or the movement diffusivity, the mass diffusivity, all units are same, all will get the meter square per second only when use this one. So, here you can take here alpha equal to K by rho Cp, alpha equal to K by rho Cp, K you know watt per meter Kelvin, K here, you know rho is the kg per meter cube density. I am just showing how we get the value of meter square per second. Then Cp is the specific heat, joule per kg Kelvin. So, the watts you can write joule per second also, that is not issue, okay. We can replace that one. So, you can just cancel it, all will get cancel, kg, then this Kelvin cancel. So, only here meter cube here 1 meter square, finally we get the value of meter square per second. So, definitely thermal diffusivity we will use for the temperature gradient in the large bioreactor, whenever the big bioreactor we are using. So, we will always use the thermal diffusivity here. I hope you understood what are the basics here. So, now we will move to little bit more to viscosity. So, what is viscosity? Already we discussed the viscosity here. So, this is a famous law, Newton's law, dou equal to mu of du by dy, okay. This is a Newton's law of viscosity. So, normally any law of laminar flow, turbulent flow always we can use here, but here the tau is the shear stress, we always call that tau is the shear stress. Then here du by dy is the, we always call velocity gradient or shear rate, this we will use a shear rate. So, normally this equation tau proportional to du by dy only. When you want to remove the reciprocal, then we have to add the viscosity, that mu, okay. So, this is a Newton's law of cooling, this is a mu of du by dy, the du by dy is a velocity gradient, the mu is a viscosity. So, the viscosity here, why you want to study viscosity, that is called viscosity coefficient, they are saying viscosity coefficient, and same way for the tau is the shear stress, the du by dy is the velocity gradient, okay. So, viscosity normally the strongly influence the pumping power requirement, because if more viscous is there, you have to spend more this one. So, they may missing efficiency of bioreactor. Of course, then they discuss about the mass transfer rates, especially the oxygen transfer, the nutrient dispersion, all the viscosity play main role. Same way for heat transfer, exchanger, cooling jacket, there also viscosity main play role. Then aeration dynamics, bubble rise velocity, interfacial area, everywhere the viscosity play main influence here. So, the viscosity has a great impact on the bioprocess design, then scale up, then operating economics. These are all the impact for viscosity here. So, just a small example, what is the, okay, some practical example, honey and water. You take honey and water, the honey having always high viscosity, the flow is very is not easy, the flow is very slow. If you take a water flow very easily, but honey flow very slowly, but because of due to high viscosity, okay. So, that is the main reason the viscosity is depend on the several factors like sugar concentration, the water content, the temperature, all play main role here. So, just for example, for cooking oil and air. So, cooking oil of course, we have higher viscosity compared to the air. So, that is the reason the cooking oil have a higher viscosity here. So, same example for the rheology in the fungal fermentation. So, here most of the see example, most of the polysaccharides, no, the extracellular makes polysaccharides here, the both Newtonian, that is called Newtonian fluids and non-Newtonian fluid, we will also discuss that one. So, then the fungal froth always they resist the fluid motion, then increasing the impeller the power demand because of the viscous, more viscous, that is one. And the same way definitely it is a poor circulation also will be there because of this one, the fungal fermentation. And then KLA, the reduced KLA, we will discuss more on what is KLA sometime. Then definitely is directly lowering the oxygen supply, which into the biomass finally the yield is will get a very less, and finally it reduce our metabolic production. So, this is a main play for viscosity, the play in the fungal fermentation here. So, here very simple, what are the classification of viscosity? So, viscosity is defined as the ideal and perfect fluid. Of course, ideal fluid, ideal viscosity is not at all there, but for whenever if you want to solve some modeling, simply mathematical model, because mathematical model we always assume the sometimes ideal flow, even when you use for thermodynamics, so we always use like ideal gas law. So, when you solve that one, we have the mathematical model we always use, but normally it is never the reality is not there. So, the other is a inviscid flow, inviscid fluid here. The term always with use the zero viscosity, because that is one. And here why zero viscosity? Whenever there are high Reynolds number, if viscous is very low. So, example I think NRE, the Reynolds number equal to dV rho by mu. If viscous is very low, if it is close to approximate to 0 or 0.01, automatically the Reynolds number value will get a shoot, because this value if we get decrease, then automatically this value increase. So, automatically the Reynolds number also increase here. So, the viscous, the value, the viscosity value whenever go close to approximate 0 or close to this one, so we will get the Reynolds number is higher, that is only they mention high Reynolds number for external flows here. The real fluids, what we are the real world we are using here. So, this we always call viscous fluids. So, here the best example for kerosene, then castor oil here. Whatever the practical the fluids all using this one, that is have finite viscosity is there. So, the where exactly the dominant effect here, the bioprocess system, especially with the complex here, the cell suspensions, the polymer rich media, all the viscous effect is more here. And of course, the microfluidics, wherever the microfluidics, where a small channel occurs, the viscous force is important, because the micro channel is always less than 1000 micron size, and whenever if you reduce the size, and then definitely the viscous also, the viscous effect also there. So, wherever microfluidics, the microfluidics maybe the effects are very less, the viscous force effects are very less, but the microfluidics definitely the viscous plays main role, that one. But I think the remember microchannel fluidics, we have different type of flow is there. One is a bubble flow, then select flow, different type of flow is there, then select flow, all type of flow is there, all type of flow, the velocity the play, velocity then viscosity also play main role. So, then viscosity of liquids is a general definition. Of course, viscosity of liquids always decrease when you increase the temperature. If you increase the temperature, the viscosity of liquids always decrease, but the gases are different, because the viscosity of gases always increases when you increase the temperature. So, normal the viscosity of water 25 degree 1 centipoise, but same way for air we always write 1 into 10 power minus 2 centipoise. So, viscosity of water and viscosity of air here. So, here we will discuss about what is the difference between Newtonian non-Newtonian fluids here. So, already we discussed the tau equal to mu of dV by dy. So, Newton's law here is a very famous law. The tau shear stress, shear stress, then this is a velocity gradient here. So, here the dV by dx here we always write n here. Okay. If n equal to 1, this always obey the Newtonian fluids. When n equal to 1, this is always the obey the Newtonian fluids. So, if n equal to less than 1 or n equal to greater than 1, that is called a non-Newtonian fluids. But Newtonian fluids, I repeat again, whenever the n equal to 1, then we will write a simple tau equal to mu of dV by dy or dx. It is called velocity gradient. So, what is the difference in velocity gradient and velocity here? See example, dV you can say velocity difference, but whenever if you write dV by dx, that we called as a velocity gradient, because with respect to distance the velocity vary. So, this we always call velocity gradient. So, here anyway tau equal to mu of dV by dy or dx, whatever just consider, and then the viscosity here. So, if you say Newtonian fluids, this is almost always constant, because the mu is not vary, but whenever is then fall in non-Newtonian fluids, definitely the viscosity will vary with respect to this one. So, what they are saying, this is a shear stress, tau they are saying shear stress, okay. Then I will erase it, okay. Tau we are saying shear stress, then the shear rate is, I will write one more time, tau equal to mu of dV by dy for understanding, okay. We will write for shear stress and the other one is for shear rate. So, here simple example how the shear flow pattern the parallel plates. So, initially the both plates are stationary plate, they kept as it is. So, considering two infinite parallel plates, but the distance separated by d, the d is here, the distance separated by d. So, initially the both fluid plates are stationary, you assume they are like stationary, okay. Then the lower plate you make it a motion, you just move it, the lower plate make it a motion, that means that you apply some shear force, this is shear force, you apply some shear force, then automatically the lower plate move here. So, whatever this velocity, this liquid also slowly get to move here, but in the upper plate, that is called upper plate, this is upper plate, okay. Upper plate the velocity is 0, upper plate the velocity is 0, v equal to 0, that means that the velocity is this not moving actually. So, the two plates here velocity is there, because since the plate is moving, definitely some amount of velocity will be here, but the top is velocity 0. So, velocity fixed here, okay, the plate is fixed here. So, then here what happened, when you move the velocity wherever 0, I think you can see here this is a graph, okay, velocity here velocity is a maximum, that is showing velocity is a maximum, but whenever here the velocity 0, velocity 0, the same place the shear stress should be a maximum, that is a composition here, wherever velocity 0, the shear stress is the maximum. Same way here velocity is a maximum, v equal to v max, then automatically the shear stress is a 0. If there is no shear stress, then velocity high, that is a very simple here. If there is no shear, then velocity always high, it move as it is, whatever this one, okay. So, other what is the covert flow? So, here that is the definitions here, whenever this flow is steady, the flow is steady, the laminar flow. I will discuss laminar flow, what is laminar flow. Normally, we define as a Reynolds number equal to dV by rho by mu. So, if it is normally less than 2100, okay, if it comes, this is always called as a laminar flow. There is a three type of flow is there, laminar flow, turbulent flow, then transition. So, if the flow is a steady, then the laminar flow, the plate motion is always called a covert flow. So, where we all use here, normally they will use for the agitation in the stirred tank bioreactor. The bioreactor here, no, the stirred tank bioreactor, the velocity profile all we have to use, especially impeller motion, they create the velocity gradient similar to covert flow near the blade surfaces here. So, what are the assumption here? The flow should be a steady, that is called a steady state, all okay, and then laminar, and as also incompressible. There is a compressible, incompressible. Normally liquid and gas we always write compressible, okay, but incompressible, the two type of gases is there, okay. So, here then there is no slip condition at the boundaries, and here there should be some finite infinite velocity, that is also another assumption here. Totally 3 assumptions are here. So, one is the flow is the steady, it is a laminar, it is not a turbulent flow, and incompressible, fall come in the incompressible. So, liquid salt coming in the this one. So, how we derived this the shear stress, just small, okay, the diagram we are explaining here, same way here. Okay. So, what is the V dt? V is the velocity, we call the velocity, then dt is the how much, okay, time we are using here, and again how much the velocity dv, the change in velocity. So, the V is the velocity, the dv is the change in velocity. So, how much this one? Here the tan d theta equal to the V of dv dt minus of this one dy, but automatically will get cancelled, the Vv will get cancelled. So, then we will get the dv dt of dy. So, anyway this the dt will comes to here. So, we can write d theta by dt equal to dv by dy. It is the angular deformation, how much, okay, this moved here. It is very simple how they derived this the shear stress here. The shear force, always the shear force, we always write tau, no, tau equal to F by A, shear this one, F by A, tau shear force. So, the proportional to d theta by dt, the how much this one. So, that is we are always writing tau, but again you want to replace, because this is the theta, the how much the velocity changes here, tau equal to proportional dv by dy. So, when you want the proportional factor to remove, of course, we have to use the viscosity, that is called the viscosity mu, mu is the viscosity. So, the proportional constant, whenever if you want to remove any proportional constant, so we have to use something that is called the proportionality constant, we call the viscosity coefficient, that is mu. If you want to use this one, then mu you have to use here, okay. We have this Newton's law here. Yeah, I think it is very simple. Again tau equal to mu of dv by dy, the mu is the viscosity, then again shear stress, shear rate, same thing what we discussed here. So, how we have to get the unit of viscosity here? Normally unit of viscosity Pascal per seconds. You just see here the tau shear stress, that is the same unit for pressure. So, there is a Newton per meter square, already this velocity is the meter per second, and again here the distance is meter. When you solve it, then we will get the Pascal per seconds. So, that is only Pascal seconds they are writing, 1 Pascal second equal to this way. So, we can write this way. So, in terms of the dimensional analysis, I think that is a different, maybe we will discuss that one. So, whenever if you want to write mass, okay, where is the mass, we always write m, whenever length is there L, whenever time is there then T, the like temperature, like that we will write a different way. So, the tau is the different type of dimensional analysis we write, we will discuss then sometime after sometime the classes. So, with here this is a shear stress, then the shear rate, this is called a shear rate. The shear rate, if you solve this one, then we will get a time inverse, okay. So, we can write even small t time inverse also. So, finally, the viscosity units here ml. So, we can write kg, m stands kg meter second, okay. The kg is a m, then L is here, then meter per second, this one, okay. So, the units viscosity is the kg per meter second. So, shear stress, shear rate in the graph. So, whenever the shear stress and shear rate is a mu equal to always 1, is a Newtonian's law. Whenever non-Newtonian is a behave different way, we will discuss sometime different classes, okay, in the forthcoming classes. So, these all behave non-Newtonian fluids, because the n is here, the n stands, n equal to 1 is the Newtonian fluids. If n less than 1 or greater than 1, these all will come as a non-Newtonian fluids here, that we will discuss sometime. So, the kinematic viscosity is a, we call as a, already the class I discussed, the alpha k by rho Cp, this unit is also meter per square second, okay. Then if you take the diffusivity, mass times the diffusivity, this is the thermal diffusivity, this we write a thermal diffusivity, then this we always write the mass transfer diffusivity, this is also meter square per second. And the kinematic viscosity mu equal to mu by rho. So, this is a viscosity, of course, you know kg per meter second, this value, then this value kg per meter cube. So, once you get cancel all, then we get a meter square per second. So, we have 3 type of diffusities there. Okay. One is the mass diffusivity. Mass diffusivity what we discussed D, that is as meter per second. Then the thermal diffusivity alpha, alpha equal to meter square second, that is a K by rho Cp, just we discussed just now. So, that also thermal diffusivity, but this we used to call as a moment of diffusivity. Moment of diffusivity is a meter square per second here. So, the units are already meter per second. It is always used for the definitely for various layer the viscous fluids here. And whatever discussed same way the Newtonian and versus non-Newtonian fluids here, if is okay, the mu equal to mu always constant whenever the Newtonian fluids, but definitely for non-Newtonian fluids, the best example for Newtonian fluids, water, some dilute salt solution, is always we take as this one. Viscosity remain constant whether shear rate, shear change changing, that is we always fall in the Newtonian fluids, but most of the liquids are non-Newtonian fluids only. So, non-Newtonian fluids whatever we discussed, the mu is not constant, because the tau equal to mu of dV by dy, the mu is a not constant, it is always vary in the non-Newtonian fluids. So, that depends on shear rate. So, here the non-Newtonian fluids we always call it shear thinning, shear thickening, and then pseudoplastics, many things are there, viscoelastics, many things is all come in the non-Newtonian fluids. Sometime we will discuss more on this one. So, where we will use the fermentation broth, then we will use the polymer solutions, then blood. Okay. All these places we will use the here. So, the non-Newtonian always, okay, most of the fermentation is one, the non-Newtonian plays main role here. Definitely we need more knowledge about the non-Newtonian fluids, then only we can get idea about the when you make a fermenter or bioreactor. Then introduction of non-Newtonian fluids same way here. Definitely this is a non-linear relationship, because I already discussed the tau, these both are varying. Okay. The shear stress, then shear rate, both will vary for non-Newtonian fluids, but Newtonian fluids always this is a constant. So, and the flow behavior same way the applied shear condition, whenever the shear rate is there, definitely the viscosity also will vary here. So, where exactly we will use here the bioprocessing here, high cell density, the non-Newtonian fluids high density, then the gas, liquid, solid, multiphase. When the gas, solid, liquid all together the multiphase interaction is there, definitely the non-Newtonian fluids is the main play role here. Then the presence of biopolymers like protein, polysaccharides, when you study this one, this definitely will come with all in terms of non-Newtonian fluids only. So, then we discuss apparent viscosity. Apparent viscosity, what is the difference between viscosity and apparent viscosity? The apparent viscosity we write as a way mu A equal to the shear stress by shear rate, the same way here, but it is definitely shear rate dependent. If whenever the shear rate get increase and the viscosity also get increase or whatever get decrease. So, that is we always call the apparent viscosity. Definitely this viscosity will vary with respect to the shear rate, that is called the apparent viscosity. It is always used for non-Newtonian fluids here. Here same just for what are the dependence here, apparent viscosity is a not true material property. It is definitely the depend what we already discussed is the shear rate or shear stress is not like constant Newtonian fluids. Newtonian fluids always the tau equal to mu of this one, the dV by dy, okay, the mu always constant, but here the mu that is only varying. They are saying that the mu is apparent viscosity, we write mu A here, tau by the shear, this will come here. So, this is shear rate we write. So, definitely it vary, that flow condition either laminar or transitional, okay, any type of this one, definitely this vary, the mu value will vary. But at the same way, so if it Newtonian fluids, of course, the mu A equal to mu, that is only we are discussing same thing, the mu equal to mu, the same, that is called independent of shear condition, the shear stress, the shear rate does not matter here. So, what are the key takeaway point here? We discussed the fluid properties like pressure, temperature, density, then viscosity, diffusivity. Diffusivity also we discussed 3 types of different diffusivity, thoroughly discussed. Then surface tension, because it is all strongly influence the mixing of aeration, then the heat transfer, the mass transfer in bioreactors. Everywhere this is a most influence this one. And we discuss also viscosity, apparent viscosity, how the major role the transfer phenomena. Then also we discuss the shear stress, then shear rate, then Courbet flow, then apparent viscosity, what we discuss here. And then of course we discuss about the very clearly Newtonian, then non-Newtonian different type of fluids here. Thank you.